please welcome Mark Rusinovich.
Good morning, everybody. Try that again. Thanks for coming. That's Friday morning, long week here at RSAC conference. My name is Mark Rusinovich. I'm the Chief Technology Officer of Microsoft Azure. And I'm here to talk about, let me see if I can make the slide go back here. Okay, title slide's missing. But I'm here to talk about open source security. And that might seem an odd thing to some of you for a Microsoft person to be coming up here to talk about open source security. Those of you that haven't been watching what Microsoft's been doing with open source security. So Microsoft, for those of you that haven't been paying attention, is deeply an open source company at this point. But then how does that relate to me, being the CTO of Microsoft Azure? Why am I here to talk about open source security? And the reason is that when we take a look at Azure as a cloud platform, a ton of it is built on top of open source. We consume open source. We also publish open source. And so when you think about the cloud provider's responsibility to our customers, they don't really care what we build our platform on. What they care about is that we're keeping them secure. And that means that with whatever we use to build that platform, the buck stops with us. If there's a problem in our own software that we create internally, or software that we're consuming, or hardware we're consuming from third parties, if there's a problem, customers expect us to deal with it and keep them secure. And so this is very near and dear to my heart in terms of what can we do to make Azure more secure, leads into the supply chain of Azure, which includes open source. I'm also here because the COVID-19 thing hasn't gotten too crazy yet, so I thought I'd show up today and risk it. But imagine a world where a hugely popular open source package gets compromised, and people are consuming it and deploying it and operating it. And the world becomes compromised because of this open source dependency. It sounds like something that is theoretical, but in fact, it has happened. And it's happened multiple times, and it continues to happen. And these are just some of the examples of open source being compromised and then being consumed in that compromised state. Some of you might have seen these. These are both from the last 2 years. WebAdmin, an incredibly popular web portal administration toolkit, this was compromised for a whole year with a DDoS backdoor and a credential stealing backdoor. So allowed the attacker to get into the web server that's being managed by this thing and deploy arbitrary software onto it. Downloaded 1 million times during that year that it was compromised. So REST client, this is a package that a lot of developers used to authenticate to REST APIs. This was backdoored to steal the credentials that came as part of that authentication. Event stream, a package that was downloaded 1,000 times or 1,500 times a week. This thing was backdoored. And then finally, Vesta CP, another control panel platform for managing websites. This was backdoored in a source control system and also served as a DDoS malware distribution platform for the attackers that got into it. These are all examples, and there's many more. Here's an example of one timeline for a very popular open source package called Bootstrap SaaS. This package has been downloaded in its lifetime 28 million times. And it was compromised, you see on this date, the package was compromised in the NPM repository, in Ruby, sorry, it's a Ruby package. It was compromised by attacker, the package that got control of it, removed the last good one, and then published one that had an exploit in it. And you can see that at the time that it was discovered, at that point, there was no last known good to fall back on because they'd removed it. And so at this point, the Ruby package management was scrambling to figure out how to get people so that knew that they were compromised to get back into a secure state. And a good one was eventually published. But you can see a total of 8 days where really anybody dependent on the upstream Ruby package management system was in a state where they couldn't get fixed if they downloaded the vulnerable package. An event stream is an interesting one because this one has a story where it shows us we're so dependent on people that we don't know producing the software that we consume. In the case of event stream, the maintainer for this event stream package, like I said, it's incredibly popular, just felt he didn't have time to maintain it anymore. And he got emailed by somebody saying, hey, you know what, I see you're really busy. I'm really passionate about this thing. Why don't you let me help? So the maintainer gave management control to this volunteer. This volunteer made some changes, published an update to it. Everything looked good. And then they introduced, after that, a dependency. That dependency was a malicious dependency that was aimed at stealing Bitcoin for anybody that was at a company called Copay off of whatever wallets were sitting there on the servers that it happened to get installed on. And that's an example of somebody kind of getting trust inside the open source ecosystem supply chain and then being able to infiltrate and get a backdoor. Now, fortunately, like this package is incredibly popular, but the fact is that it was only targeted at this particular Copay Bitcoin. It wasn't going after a general purpose compromise, in which case the effect would have been much broader. So let's talk a little bit about the agenda, because I think the way that you have to frame the problem, and by the way, I want to make it clear that the problems that I'm talking about aren't specific to open source in many cases. They're general software supply chain problems. The fact is that open source is such a massive ecosystem that we need to go after it specifically, and there's some specific implementation points in the supply chain that need to be addressed for open source. So let me talk by framing the kind of whole problem about how we consume software as a supply chain, and then I'll get into the various steps of that supply chain, what the issues are, examples, and what is happening for open source ecosystem to help address those points in the supply chain. And I'll start here by talking about supply chain in the context of a food supply chain, which is one that we're all familiar with. A farmer's growing crops, a buyer's purchasing those crops, a distributor's taking and shipping the products into stores, and then a customer's buying them. And if you map this onto software, and open source software, you've got open source developers. There's source code repositories where they're storing their source code. There's application developers that are consuming the output of that source code, and then they're providing an end product to their customers. This is the simplified form. It's actually much, much more complex, and this is what makes the problem especially challenging, because along this supply chain, there could be dozens, hundreds, or even thousands of participants and different points of different source code repositories, package management systems, consumers, products, and other distribution points. And there's many loops here as well. But if you take a look at from this framing, then we can go after specific parts of it. And the question when you're consuming from this supply chain, and this one applies to us in Azure, is how do we prevent unwanted products from entering a supply chain? How do we make sure that only packages and source that we've got some assurance are trustworthy enter our supply chain? How do we know what's in our supply chain? That begs the question. And how do we ensure that what we know about that supply chain is reliable? When somebody says this is trustworthy, hey, I've done code reviews on it, I've got MFA in place for checking in source code, how do we know that that's really truly the case? And then what do we do when there's a vulnerability? How do we identify what's affected by that vulnerability, and how do we roll back to a good version? So those are all the kinds of questions that we've got to answer when we take a look at this from supply chain perspective. So first, how do we find vulnerabilities? How do we help the open source ecosystem find vulnerabilities in the source code at the source, kind of where the crops are being made? And if you take a look at from a crop perspective, this means how do we end up finding that there's E. coli somewhere in those crops before it gets out. We need to stop it from even getting in there in the first place, or if it gets in, stopping that from getting down into the supply chain. And when we talk about vulnerabilities in source code, this applies to open source and closed source as well. There could be credentials in the code. There could be improper validation of inputs. There could be ability for an attacker to upload arbitrary code and for that to be executed by the code. And there could be denial of service opportunities where you're taking a dependency with a customer-facing piece of source code, piece of open source or closed source, and it's got a vulnerability that lets somebody bring down your whole service. One of the ways that something can get into the supply chain that's malicious is a technique called typo squatting. This has been known as a problem, especially in the Node ecosystem where package names are extremely short. Has anybody ever used one of these packages in your open source projects? So maybe you have, maybe you haven't, but they all kind of look generic, and they look like, if you're looking for something specific, like I'm looking for the date util for Python 3, and you know that there's a popular one out there, you might go and pull this one. But the fact is that these are variants on well-known packages that are popular in the Python community. And you can see crossfed date util instead of Python 3 date util. And this kind of typo squatting is a way that we've seen compromised open source get into the supply chain. There's been efforts to go figure out how we can prevent typo squatting. There's something called the Lichtenstein diff delta, which looks at how close words are to each other. And there's been proposals to say, hey, we don't let packages come in that are too close to existing popular packages in terms of that delta. But the fact is, when it comes to Python and Node and others where they've got very short names, makes it very difficult because this graph shows that a huge number of packages have very short distances between each other of well-known packages. And so this is a tough, challenging problem. How do we keep developers from getting compromised versions of things that have names close to what they're looking for? Static code analysis is another very popular way to go and address vulnerabilities. Looking for the vulnerabilities in the code, scanning automatically during the CI/CD pipeline, really stopping the vulnerabilities from getting into the supply chain in the first place. And there's a few different open source efforts or products, services that open source publishers can take advantage of and open source consumers can take advantage of to make sure that vulnerabilities haven't been entering them through this. One of them is called Synopsys, which looks at every line of code and execution path looking for vulnerabilities and flagging them. And you can see that it's got a huge number of vulnerabilities you can see that it'll check for. And as is common in many cases, for open source projects, this service is completely free. And so this is something that's just easy for somebody developing open source to take advantage of. And it's, why not do this if it's going to make your code more secure? Microsoft purchased GitHub a few years ago, and one of the purchases GitHub has made since that time is a company called SEML. SEML is a source code vulnerability analysis platform based off of a language that's been renamed to CodeQL for Code Query Language that lets you do variant detection on common vulnerabilities. And so the idea here is that if a vulnerability is detected in a piece of source code of a certain pattern, that you can write a CodeQL query that will find not just that specific version of the vulnerability, but also variants that are close to it through the query language that has regular expression type syntax as part of it. One of the services that GitHub is offering for open source developers is something called Security Lab, which for open source projects is free, and for research projects is also free, which lets you go and scan open source projects using SEML queries, CodeQL queries, a growing ecosystem of them. So there's a full ecosystem of CodeQL queries that look for very common and exist a kind of vulnerabilities that have already been seen in source code and lets you find them. And then there's Snike, which is a way to stop open source vulnerabilities from getting into your supply chain, ones that you might be consuming as a developer. If you're going to pull from a package and that package has a known vulnerability, this will let you know. It will also scan your source code repos looking for package dependencies and let you know if you've got vulnerabilities. And again, this is something that is completely free for open source repos. I want to show you a quick demo of CodeQL so you get an idea for the power of this for open source projects. So I've got a GitHub repo here for a project called Java Test. And you can see I've made a pull request on it, which is labeled with a name that describes just how bad this thing is, allow user submitted content. And if I click on that pull request, because I've enabled SEML scanning or CodeQL scanning on this, those scans have identified a problem. This pull request introduces one alert when merging. View it on lgtm.com, which is where the free CodeQL service is hosted. And at this point, what you can see is it will show me right in the source code the vulnerability and the path of the vulnerability. And I'm not going to spend time diving into the source code here, but what is happening here is that it's taking unsanitized input from the user, deserializing that, and then executing it. And that's this execute right up here, mona.dance. And it's basically deserialized this untrusted input into this dance method. And this is very obvious, of course, but just here for demonstration purposes, if I say show paths, this takes me and shows just the snippets of code from the source, here where the get input stream right there, which is the untrusted input, into the deserialization, and then finally how that gets packaged up and made part of that method. And all of that is just right there at your fingertips. And you can see which queries you've enabled on your open source repo. And the built-in Java queries that have been enabled on this one include, for example, character passed to string buffer or string builder constructor. And this comes with a description of the type of vulnerability being scanned for with an example of it, as well as recommendations on how to avoid or fix these kinds of problems. So very powerful tool, and you can, like I mentioned, it is an ecosystem of these kinds of queries that has been built up. Here's the GitHub repo for the CodeQL queries that are available, and a bunch of different languages available here for CodeQL to go query. And again, completely free for open source development. So let's go back to the presentation. Now, one of the other types of vulnerabilities, very common both in closed and open source software, is uninitialized variables. And one of the ways to fall into the trap of uninitialized variables is uninitialized heap and stack, which is hit, especially native code, C and C++ code, very commonly. Heartbleed is one great example of it, where uninitialized buffer, you could trick the OpenSSL server into passing a buffer back that was longer than it had been filled in with legitimate content, and then see what was beyond it. And what was beyond it could be information that would allow you to steal credentials and keys and compromise other users of that site. So there's been efforts here that have taken place, and the reason that I mention this is going after eliminating entire bug classes and doing it in a way that gets to the heart of open source ecosystem supply chains, which include compilers like Clang. And so this is an effort that's been supported by Microsoft and Google and others to go and modify these to default to initialization. And one of the reasons why these compilers historically have not initialized is because of performance concerns. Going and zeroing memory is a waste if you're going to just immediately overwrite it. But then you end up being susceptible for something like a Heartbleed. So the goal here is to change the default to initialize to zeros, and then somebody that sees a performance issue with that understands that they've not exposing themselves by disabling it for a particular initialization buffer can go and disable it if they need to for performance reasons. Yeah, and here's just an example of a tweet by one of my heroes, actually. Let me pull it back. John Carmack himself getting bit by these things. Number of days since uninitialized C++ variable caused me grief, 0. So this is something that even professional developers who have been in business for a long time get hit by. Another way to go find vulnerabilities is through a technique called fuzzing that I'm sure everybody in this room is aware of. Lots of different types of vulnerabilities can be detected through fuzzing. The question is, how do I get access to a fuzzer, and how do I get access to the platform that will fuzz my code automatically? And in the open source world, Google stepped up here and has created a platform called OSS Fuzz, This is a free service for open source projects. You go and request access to it. You provide a pointer to the repo. You provide an email address with the maintainer. And then once you get onboarded to it, your code gets automatically fuzzed by this service. And you can see that it's been incredibly successful, 17,000 bugs and 250 open source projects already detected through this fuzzing service. And it supports a number of different fuzzing engines. It supports C++. It supports Rust and Go. And so this is an example of the kinds of efforts that we really support to get the whole ecosystem in a better place. So let's talk a little bit about dependency management now, because we've taken care of trying to keep the vulnerabilities from getting into the supply chain in the first place in those crops. But how do we then determine when there's a vulnerability that's been exposed, where that came from, and what's impacted by it? And so this is all about supply chain. Here's a great example of supply chain in action in an open source ecosystem. Electron, which is the rendering engine underneath a bunch of popular products, including Visual Studio Code, Atom, Slack, Discord. This had a vulnerability introduced into it inadvertently that allowed the integration of Node.js to be enabled. So by default, when you're running on one of these platforms like this, it's disabled, and it's disabled because enabling it allows somebody accessing the interface to deploy arbitrary node code, JavaScript code, and execute it as system in the context of that app. The vulnerability that was introduced here allowed an attacker to override that control and turn the setting to allow execution of arbitrary node code. And that would then allow the attacker to take over the site. And you can see the downstream dependencies on something like that. Every one of these projects that depended on that upstream Electron with that vulnerability now had to go and remediate. But the first question is, how do you even know that you've got this dependency? How do you know that there's a vulnerability? And then how does the whole supply chain, all the way through all the dependency chains, update in a way that gets everybody as secure as possible? And one of the questions this highlights is, one of the issues this highlights is just how deep dependency chains are in the open source world. So here's a little snippet of code where I'm actually depending on the Express web server. And this looks like I've introduced one single dependency. So now all I have to do is monitor Express, and if Express is showing that it's not got any vulnerabilities, I'm good. But actually, the story is a little bit deeper than that. Because once I import Express, I actually import a whole bunch of other things with it that it's dependent on. In fact, here's the dependency list for Express. It's got 48 packages that it imports for its use. And so what I've just done by importing Express is import all of these. And I've imported all of the source code development practices of all of these packages. I've imported basically all of the contributors to all these packages as well, and their intentions, which are hopefully benevolent. Now I'm dependent on all of that. I came across this tweet last month. This is npm install, what somebody likens it to, because the Node ecosystem is one of the ones that has the deepest and broadest number of dependencies. And the reason is because people just import little snippets. And so a single project can literally import thousands or tens of thousands of these little node packages to make up a reasonably sized piece of software. In fact, let's just do a survey here. What's the average number of packages trusted by installing one node package? Anybody want to take a guess? 40? Anybody else? 60? And the answer is 80, so not too far off. And the interesting trend we're seeing with this in these ecosystems is that once something gets popular, it gets even more popular. So this is the average package reach over time. You can see as packages in this ecosystem have gotten more popular, the reach of these packages in terms of the number of services, other packages that take a dependency on them, has continued to grow. 80 was just the average, but you can see the tail goes up into the hundreds. And here's the top 5 most referenced packages in the node supply chain. And you can see that you're talking now 150,000 dependent packages on one of these. So vulnerability in one of these and the downstream effect is pretty monstrous. Here's another great example. You remember when we took a picture of a black hole last year? That was kind of a cool event, and it was done all with open source software. Here's the project, EHTIM, EHT imaging. Now, the interesting thing to note about this is if you take a look at the number of contributors, 15 contributors on this project involved with developing the software that could go and analyze these images and basically photograph a black hole. But if you look underneath the hood, because of all the dependencies they took on other packages, there were really 24,500 contributors to this project. So this truly was a much broader ecosystem effort, really. If you take a look at everything that was used to build this, went way beyond the original 15 contributors. So how do you know what your upstream dependencies look like? It depends on the type of software that you're using, of course. One of the tools that in the node ecosystem for looking at this, which is a free tool to go use, it's an interactive tool where you can go take a look and get an idea for what you're dependent on. But there's many automated tools out there for the different ecosystems that you should consider using. Let's go take a look at this one. And you can see here the URL is npm-brufa.com. And up here, you can enter a module name, and it will go look at the dependencies it's got and show them to you, and then also show you the contributors that were involved in making those dependencies. So anybody got a node pack? Anybody here a JavaScript developer? Let's raise your hands. So, okay, name a package that you use. Singular? Angular. Okay, Angular. I don't know why that's not coming up with a 0 dependencies. I don't know. That doesn't make sense. Let me try. Make sure this is working. Yeah. I don't know why it came up with 0 dependencies for Angular. Maybe it's fully self-contained. But Express, which we were looking at earlier, 48 dependencies, 56 maintainers. I was curious, like NPM itself, what that looks like. So when you run NPM for NPM install, you're actually taking a huge set of dependencies, 380 dependencies. And the number of developers, 188 maintainers. And I want to make clear that that's maintainers, not contributors. So the number of contributors is probably in the thousands or tens of thousands. So all of this isn't feeding into your supply chain. When you run NPM on your server, you're dependent on all of that. All right, let's go back to the deck. So takeaway for this section is automate your dependency mapping. In your build pipelines, apply those tools that can go identify dependencies so you understand what you're dependent on, which will come in use when you're looking for vulnerabilities. It also becomes useful when you're looking at importing things and making sure that they adhere to the policies you defined, and that they're also being maintained in a way that doesn't allow vulnerabilities to get into your supply chain. Let's take a look now at build systems and package managers, because this has been another area where, in the open source ecosystem itself, this is kind of like going to the grocery store and compromising the product there by putting some chemical on it, and now people are walking away with it. Because the farmer did the right thing, made sure there's no E. coli, the shipper got it to the store in okay shape, but at that point now, the consumer is walking in and picking up a bad product because the attacker was in the grocery store. Same thing can happen here. And there's been multiple examples here of the open source supply chain getting compromised at this point in the supply chain. Here's an example here where an account was compromised, and this allowed somebody to put a backdoor into a specific package, the REST client that I talked about earlier. This REST client, incredibly popular, And the kind of cool thing about this is that the developer, the maintainer of the REST client package, basically lived up and stepped up and said, hey, this is my fault. Here's the Hacker News thread where they're like, hey, everybody probably knows right now that REST client's been compromised. The reason why, I was reusing credentials. It's a project that I've started 10 years ago. Before I had Password Manager, and that password was compromised through some other site. I reused password, and so that'll let somebody get in and compromise this REST client. So they were producing good software, but at this point, the attacker was able to get in and compromise the package in the Ruby Gems package manager. Here's another example. This one, though, goes right to the heart of the source code distribution for Canonical's Ubuntu distro. So this isn't a problem just for the guy that's maintaining something in their spare time and kind of not applying best practices, but even major companies that are very involved with the open source ecosystem, have major impacts on it, can make these kinds of mistakes. So how do we help everybody step up here? Well, and the answer is to step up and to get into multi-factor authentication. Now, all of the package managers, the popular package managers support multi-factor authentication. All of the popular source code repositories support multi-factor authentication. And this is something that we absolutely have to start moving towards mandatory enforcement on. It is just beyond the point where we can just allow people to introduce problems through the supply chain because they just feel that multi-factor is too onerous for them, because they're having an effect on this massive downstream ecosystem at this point. Another example where problems can show up is in build tampering. So the artifacts get produced, and at that point, as the build system is packaging things up for release, the attackers compromise the build servers or the release management servers and introduces problems. And the web admin case that I talked about earlier was an example of this. So the source code in the repo, the master repo for web admin in GitHub was fine, but in SourceForge it wasn't. And this allowed the attacker to get in and put a script because they put in a script into the build server to inject the backdoor into it. So this is an example of kind of in the middle of the supply chain, the producer of the software is doing the right things, but the server was compromised. The server could be compromised even if they were following all the best practices for securing that server. But how do you detect that is kind of the question. One of the tools that we've got at our disposal for detecting these kinds of problems is something called reproducible builds. And this is something that Microsoft's involved with pushing the industry towards. Microsoft's been involved with reproducible builds for its own software for some time. Windows is now reproducible, or at least large parts of it. What reproducible builds give you is the ability to take some source code, and if somebody can rebuild it and know that given the compiler, given the artifacts that are pulled into it, that when they do a build, the artifacts are going to have specific hashes, then they can verify that if somebody says, here's a legitimate build, here's the hashes for it, they can verify that nothing's been tampered with by rebuilding from the source, that nothing got into the middle of that supply chain from build to release management. And so the Linux itself is moving towards the reproducible builds itself. The problem with reproducible builds is it's a very tough, challenging technical problem. The build has to be entirely deterministic. And one of the challenges Microsoft had in making reproducible builds was getting timestamps out of the Windows binaries that were signed as part of the signatures. And so if you take a look at the timestamps now in Windows binaries, they're completely garbage. And that's because they needed to be made garbage effectively. They're not timestamps anymore because we needed to get to reproducible builds. And so that's just one example of the efforts now the whole ecosystem needs to take to get to a place where we can have reproducible builds across all these different technologies. Another way that here in the supply chain problems can go wrong is somebody yanking or compromising the distribution units, the package manager. And this is a great example of this one. This package called leftpad, that's a node package called leftpad. It's just about a dozen lines of code for left padding a string, got incredibly popular. It's been leveraged by basically the whole web was dependent on it at this point. Back in 2016, the maintainer of that little snippet of code had another package called Kick, and there was a product called Kick. The lawyers for that product said, hey, you're violating our trademark. The maintainer of LeftPad said, I don't care. So the lawyers went to Node and said, hey, pull this guy's Kick package off of Node with a legal order to do so in violation of that trademark. So Node pulled that Kick package. When the maintainer found out of LeftPad and Kick found out about that, they got upset and they said, okay, fine, I'm pulling everything that I've got off of the Node package manager. And they were maintaining at that point about 100 different packages. They pulled them all off, including LeftPad, which ended up breaking the world. And so at this point, you can see that, that Node took this very unusual step to unpublish that package. That's down there in that tweet right there. We've took the unprecedented step of unpublishing. And I think at this point the maintainer wanted to unpublish the package, but they'd already lost control of it, so they couldn't do that, fortunately. But this restored people's build systems now that were so dependent on this LeftPad little snippet of code. So the goal, the lesson here is to mirror your repositories. This is an effort that we've been taking internally at Microsoft, and this is a very tough one, to go find all the places where people are pulling directly from public repos into their build systems versus setting up mirrors and pulling from the mirrors. And the fact is that mirrors have a couple of different very valuable properties. One of them is availability. If the upstream package repo has a problem, it goes down for availability reasons, or it goes down because it gets cut off from your build system for some reason, you've got a place to go to. But the other more serious reason for security purposes is if there's a compromise of that upstream system, you can shield yourself from it. You're one level of indirection, and so you can sever and stop mirroring the compromised vulnerability. In the case of that package that was pulled, you've got a copy of it locally. In the case of that package, the SaaS, Bootstrap SaaS package that the developer pulled the last known good version, you've got a copy of it. So you can continue to build securely in the face of a compromise somewhere in the supply chain. So it is just a very good best practice to mirror your repos. Now, this next topic, I think it really gets to the heart of addressing this problem, because we've talked about ways that developers can go scan their source code for vulnerabilities. We've talked about the way that package managers should use multi-factor authentication, and the way that you should be using mirrors if you're consuming open source software to insulate yourself from problems at that point of the supply chain. But one of the challenges we talked about earlier in the supply chain is really, how do I make sure when I'm consuming things that it has followed best practices, that the developers have used MFA, that there was vulnerability scanning that was performed? How do I check all that? How do I ensure that it was done with a reproducible build? And what were the reproducible build artifacts that were used to build this? All of these questions require the supply chain together to cooperate in having this information flow downstream to whoever eventually is going to consume it. And the effort that has started in this space is something called software supply chain, software bill of materials, which lets you answer these kinds of questions. Where did things come from? So who produced it? Is there a strong identity? Do I trust them? That way I can say I trust these publishers. What is the product itself? And this is one of the challenges in open source ecosystem. If you've ever seen vulnerability in package version blah, well, what's the source code that fed into package version blah? Maybe I've consumed that directly. How do I know that that's been fixed? How do I know what other dependencies that source has? What other packages depend on that vulnerable piece of source? Those are all questions that having some kind of tracing of this source was used to build these things would let you go back up and answer those kinds of questions. Licensing is one of the questions that enterprises have around when they're consuming open source software or when they're modifying open source software and then redistributing it. Is it MIT? Is it BSD? Is it what license is it? Am I violating it? Am I being conformant with it? And then, like I mentioned, how was the product created? And then what materials were used to build the product? So software bill of materials, which tracks all this information as it flows down the supply chain. Let me give an example of how it might defend against advanced persistent threat sitting on a build server. Developer commits some code. The build system builds the artifacts in the normal path. The release management system takes those artifacts, packages them up, and then sticks them in package manager, or it releases it as part of a product. In the malicious case, we've got somebody that's tampering with those artifacts in the build system. And this is like the web admin case, for example. So the release management system creates a malicious build from that release, and then everybody downstream is compromised by that. If we had software bill of materials in this flow, the developer commits the code, the build system compiles the code, it generates and signs the software bill of materials, that gets and publishes the build artifacts. The attacker then tampers with those build artifacts. The release management creates a malicious release from that build. It's malicious because some of those have been compromised. Now, downstream, the release management system attempts to verify that the malicious artifact was against that signed SBOM and sees that the artifacts don't match. The ones that came from the build system don't match the ones that were published by the release system. And at that point, it says, wait a minute, something's been compromised upstream, so I'm not going to release this. Another example is just making sure that there's policy gates in place. The software that I'm consuming had to go through specific code verification, either static vulnerability analysis or check for credentials in the code. How do I know when I'm consuming the software that that's the case? And again, with software bill of materials in the mix here, make sure that what's being consumed downstream matches those policies. We won't release software that doesn't adhere to these policies. I don't want to trivialize this effort. If you take a look at what's required here, it requires massive changes to infrastructure everywhere to support software bill of materials. But the fact is that we, Microsoft, Google, others, have all come to the conclusion that this is absolutely necessary. And so this massive industry-wide effort at this point to, first step, define a software bill of materials and then standardize it. And there's a couple of projects already in existence for this that could be suitable for this. One is called SPDX, Software Package Data Exchange, which has a declarative format. It was originally targeted at licensing, tracking licensing through supply chain. But they're now looking at extending this to support the requirements for software bill of materials, including strong signatures, identity, and policies that can go along with it. Another one is called InToto. And InToto was created specifically to address or to target the security side of the supply chain with the software bill of materials, where they've got different personas, and those different personas can apply policies, can leverage the InToto tools through their build systems and release systems to augment the artifacts with InToto SBOMs. And those SBOMs then can be verified against policies using, again, the InToto tools. The goal here with all these companies looking at this is to come up with, let's come up with a standard SBOM specification, and let's get that adopted as an industry standard through NIST or some other means. And then let's have the whole ecosystem start building, tooling, and putting this in their infrastructure so that we now have this information flowing for everybody. I want to give you a quick demo of InToto and show you kind of what it can do. So I've got Visual Studio Code here, and I've got a package here that you can see I'm using the InToto run. I'm going to clone a GitHub repo called Demo Project Jekyll. And I'm going to CD into it. And what happened right there, by the way, when I did that clone, InToto, because it was monitoring it, is keeping track of every command along the way and the artifacts that were produced in that command, including their SHA hashes. So detailed tracking, I'm going to move that into this folder called verification. And the next step is I'm going to run a linter on it. Right here, an HTML linter. So this would be me doing a static code verification on it. Again, that is going to end up creating this linter artifact for that command, the same kinds of artifacts there that we saw, annotations. I'm going to copy that here into the verification folder. And then the final step is to do a Docker build on this thing to build it into a container. And now I've got my Docker build, and I have the one last there, in toto artifact, SBOM artifact that I'm going to drop into the verification folder, if I can reach it from here. And there we go. And now at this point, I've got all those artifacts there. What I can do is run this in toto verify on the whole project. And looks like I've made a mistake. Well, what should happen is that this doesn't find any errors. I've made some mistake in the flow here. But you get the idea. Really, what this should come back with is a verification of the artifacts against those hashes. And I can even have a policy file that says I want these policies, which are also signed as part of those artifacts, to be enforced. And in toto would ensure that that's the case. So that's a quick look at in toto. So finally, let's talk about responding to the threats. Once there has been a compromise someplace, and there will be more compromises, even with all of this, and when it comes to food compromise, everybody gets food safety alerts. Goal is that find the original crop where the E. coli came from and ban only everything that came downstream for that, not just all lettuce in general, ideally. Same thing happens here, is we need to understand both this impact, the severity of the vulnerability, as well as what parts of the supply chain are impacted by it. So this is part of tracking the contaminants through the supply chain. Everything that I've talked about earlier up to this point feeds into this, especially SBOM. With SBOM, with the strong naming, with the hashes, with the source attribution, we can change. Ideally, in a world where everything's flowing through SBOMs, downstream at your code, you can check a look at all the bombs that have come with the things that you've pulled dependencies on, and go all the way back upstream with automated tooling back up to the source files. I had asked that question a little bit earlier. When there's a vulnerability in a package, and that vulnerability came from a piece of source code, what other packages dependent on that source code? That is something that SBOMs ultimately can answer, just through automated walking back through the chains of dependencies in the information in this metadata. So just want to emphasize how useful this is. Now, that's not to say that some of the other things we've already talked about that are in place and you can take advantage of today, like these automated dependency tools, to say this package I depend on, what projects of mine are leveraging it so that I can go make sure that they're all patched and using the latest version, are useful and today before we get to this world of software supply chain. But at least for the projects that you start up, if you're producing open source, recommend that you already start looking at getting SBOMs just for your own hygiene. And that's software bill of materials. So brings me to one point I want to make here, and that is the way that we look at open source security is this isn't something that we want to differentiate on when it comes to Azure. Really, our goal is to lift all boats in the whole ecosystem here. And this is why we're working with a bunch of other companies, including some that I mentioned, on this problem, and why I'm here to socialize this problem and to tell you that there's growing efforts across the industry that you should be lookout for chances to participate in. The fact is that none of us are competing on the security of open source. We all want to make it better. Making it better keeps us our software more healthy, our services more healthy, and keeps our customers secure and healthy as well. Now, just the concrete things you should take away from this today, besides the fact knowledge and the fact that things are happening and that you should be looking out for ways that you can participate more deeply in these things, like the SBOM effort, is if you're producing open source software, actually if you're doing anything with anything in software or systems, enable multi-factor authentication, run static analysis tools, onboard your project to reproducible builds, understand your dependencies, and as a consumer, know what you're consuming, automate the mapping of your open source project dependencies, learn more about software bill of materials, and this is a very critical one. I think if you've got a mission critical business where you need to be able to build something at a moment's notice, or you're building product, you need to be able to update it regularly, and you're dependent on upstream open source, is mirror those repos, mirror those package repositories. Is one of the big takeaways from that. So brings me to the conclusion of the talk. I hope you found this informative. I hope this opened your eyes if you hadn't been aware of the kind of issues here that we need to go address together, that this is more real for you, and that now you're walking away with something concrete to help your open source security posture, and even proprietary source security posture as well. But looking for, again, big takeaway is participation from the whole ecosystem is required to get us to a better place. So with that, I want to thank you very much. Hope you had a great RSA conference, and hope you stay healthy yourself. Thanks.